Hi, Stu from Music Technology here. In the last video, we looked at the output stage of the Big Muff Pi pedal located here in this particular version, and we did a DC analysis and worked out some of the currents and voltages flowing through this section and the gain. Today, we're going to do a small signal AC analysis of this section of the pedal. Now we can measure the output impedance fairly easily because we're connected to the output of the pedal, so we can measure it. But the input impedance is slightly more tricky because we're connected to the rest of the sections of the pedal. So what I've done is I've built up a version of this stage on the prototyping pedal here, which will allow us to take some measurements and maybe compare them with the actual pedal here. So let's get going. Okay, so let's start by looking at the common emitter topology of the output stage of the Big Muff Pi pedal, and I've drawn it out here. You'll see that it looks exactly the same as the linear power booster circuit. So what we need to do to make an AC analysis or small signal analysis is first short DC power sources. So our 9 volts becomes ground to an AC signal. And we need to short our capacitors like this. Now we've done that, we can further simplify and redraw this circuit. For example, bringing this resistor down in parallel with this resistor and then working out the parallel resistance of R1 and R2 as we did before in the linear power booster video series. So let's do that next. Okay, so now we've grounded those resistors, we can redraw them down here. Now this will make more sense, of course, if I name these resistors. So this is R1, this is R2, this is connected to the emitter, so it's obviously RE. This is connected to the collector, hopefully you can see that, that's RC, and this is our output potentiometer, and we're going to call it RV1. Now hopefully you'll notice that these two here are in parallel. So we can say that this resistor here is R1 in parallel with R2. And then this is RE again, this is RC, and this is RV1. And that just keeps things more simple for our calculations. Now we can work that out. So we know that R1 is equal in this stage to 430k and R2 is equal to 100k. And we got those values in the last video when we analysed the circuit and did our DC analysis. Let me just jot down some of the other values so we know what they are. So RC in this circuit is 15k and RE is 3.3k, or 3k3 is another way of writing that. And RV1 is 100k. And I think it's linear in this circuit actually, so I'm going to put B. So we need to use our parallel resistor equation to work this out. So that's 1 over the total resistance equals 1 over, in this case, R1 plus 1 over R2. So 1 over the total resistance, or the reciprocal we call that as well, is 1 over 430 kilo ohms plus 1 over 100 kilo ohms. So on my calculator, I can do that by going, first of all, turn it on. I can say 430 times 10 to the 3, because it's kilo ohms. And then press this button, which is to the -1, which is the reciprocal, same as doing 1 over, plus 100 times 10 to the power of 3. The K is 3 zeros, of course, so it's 100,000, and then to the -1, which is the same as 1 over, and then our equals. And then I do this answer here to the -1, because I need to take the reciprocal of that, and press this button here. So if you get a fraction as your answer on your calculator, press this button, and it's 81.1k, so equals 81.1 kilo ohms. Now that's going to be the approximate input impedance as well, but we'll work that out in a slightly better manner in a moment. So R1 in parallel with R2 equals 81.1 kilo ohms. RE is 3k3 RC is 15k, and RV1 is 100k. So we can build on this now, and what we'll do is we'll look at our hybrid pi transistor model, which we were introduced to in the linear power booster videos, and we will try and work out some of the AC characteristics, or the small signal characteristics of this circuit. I'm going to stick to the hybrid pi transistor model for this analysis because we've looked at it before in the linear power booster series. Now, if you don't understand any of this as I'm going through it, because I'll go through it a little bit faster than I did in that series, I encourage you to go back and watch the linear power booster analysis and then come back to this analysis here, because there's a bit more explanation in that video. So I've written down some of the equations that we need to know. So we've got this model of a transistor here, which is a voltage controlled current source. Here's my current source, and that's beta IB, otherwise known as IC, or the collector current. You can see it's connected to the collector resistor here. We've got our emitter resistor here, so you can see that this is the emitter. Let me write this in. Try that again, shall I? Emitter, this is the collector, as I just said, and this is the base. So we've got this resistance here called R pi. It's important to note that this is not actually a resistor, it's a resistance. So we need to calculate the value of R pi in order to be able to calculate things like the gain of the circuit in a more effective manner, and we can compare it with the gain result we got in the last video. So in order to do this, what we need to do is take beta, which we know to be 400, as I've noted it here, and divide it by GM, which is the transconductance of the transistor. Now, we don't know the transconductance of the transistor yet, so we need to calculate that as well. Now, fortunately, there's a fairly simple equation for doing that. It's transconductance, or GM, equals the current at the collector, which is the same as beta IB. It's the same, it's two ways of writing the same thing, basically. IC equals beta IB. So, as I've noted here, beta IB or IC, and we found that out to be last time 303 microamps. So I'm just going to call it 0.3 milliamps. And then we've got this value here, which is VT, which we discussed during the linear power booster video, and it's the thermal voltage of the transistor, and you'll be pleased to know that it's always roughly 25 or 26 millivolts for this type of analysis. So we can say that GM equals IC, which was 0.3 milliamps, over 25 millivolts. So we can do that now. So we could just do 0.3 a minute divided by 25, and we get 0.012 Siemens, which is what the unit of transconductance is. It used to be called mhos as well, which is ohms backwards because it's the reciprocal of ohms. I might come back to that in a future video, but we will stick with the SI unit, which is Siemens, 0.012 Siemens in this case. But let me just show you if I do the full input of the full numbers here. So 0.3 times 10 to the minus 3, because it's milliamps, divided by 25 times 10 to the minus 3 millivolts. And we get 3 over 250, or 0.012. And if you note, the times 10 to the minus 3 cancels out. So the millis cancel each other out here. So that's why we've got the same result. So our transconductance equals 0.012 Siemens. Now we can plug that number into our R pi up here, and we can say R pi equals 400 divided by 0.012. So 400 divided by 0.012 equals 33.3333 recurring. I'm going to press the engineering button. So you can see there's 33.3 recurring times 10 to the 3 is obviously kilo ohms. So we've got 33.3 kilo ohms. So let me change the colour and we'll write that in. 33.3. Okay. So now we know the value of the resistance of R pi using the thermal voltage and the transconductance. So now we can use that to get a better approximation of our gain here. So the gain before, so we calculated it before as minus 13.14 decibels for this stage, and that's a very good approximation and probably good enough for this. But seeing as we've calculated this now, let's plug it into this equation and see if we can make that a little bit more precise. Now obviously in reality we're going to have tolerances on resistors and things like that, so it's never going to be really precise. So this is only ever a rough approximation of what's going on in your circuit, and we can then measure what's going on as we've done before in these videos. So RC I need first of all, which is 15k, and then we're dividing that by RE, which is 3k3 plus 1 over, and we calculated the transconductance to be 0.012 Siemens. So we've got 15 times 10 to the 3 because it's kilo ohms, and that is divided by, and I'm going to use brackets now, so it does this equation first, 3.3 times 10 to the 3 plus 1 over 0.012, and if you just thought you could use to the minus 1 as well to get 1 over to get the reciprocal, you're of course correct. This is just another way of entering it into the calculator, and we get a number that doesn't make sense. Now why is that? To think about this for a second. So we've got 4.43 as our gain. No, that's right. Yes, that's right. That's the voltage gain. So the voltage gain is 4.43, and then we need to go 20 times the log of 4.43 to get it in decibels like we've got up here. So there we go, 20 times the log to the base 10 of our previous answer, close brackets, and we get 12.93, or it's actually minus 12.93 because it's an inverting amplifier. And you can see how that value is close to that value, but it's actually not quite as much gain, which is what you would find in reality. And we'll measure this in a minute and see how close we are to either of these figures. Now the other thing we can do now is calculate the input impedance of this stage, and I've written the equation up here. Now we can roughly do that anyway. It's R1 in parallel with R2, which we calculated to be 81.1k. But now we know R pi, we can add it into the equation. So it's R1 in parallel with R2 in parallel with R pi plus beta plus 1 RE. So we know we've got 81.1 kilo ohms, and it's in parallel with R pi, which is 33.3k, and that is added to 401, which is beta plus 1, multiplied by RE, and RE is 3k3. So you can see that this resistor here does make a significant impact on your input impedance, or Zin. So I'm going to do 401 multiplied by 3.3 times 10 to the 3, and I'm going to get the answer for that. So I've done this bit of the equation here. Then I'm going to add that to 33.3 times 10 to the 3, and I'm going to get 1.356 megohms roughly. or 1.3566 mega ohms, should I say. Now we want that in parallel with our 81.1K. So I'm just going to go 81.1K in parallel with 135.66K. Nope, that is wrong. 1356.6K, just to keep the units the same. I could write 1.3566 M if I wanted to use mega ohms. Now what I've got to do is take the reciprocal of that and then add it to 81.1 times 10 to the 3, reciprocal of equals, and then we'll take the reciprocal of that, and we get 76.5 roughly, 76.53 kilo ohms is our input impedance. So you can see how close it is to 81.1, but it does make some impact on the input impedance of the circuit. Now note there, I had to think about my units as I was going through this, and I thought I'd just leave those mistakes in this time because that often happens, and there's things that throw up, such as this 4.43 here, where you think that's not right, it's not the same as this, but then thinking through it logically you realise you've missed a step or you've miswritten down a number, and I've just left that in there because it's natural for that to happen. And the more you do this, the more you'll write the number and you'll think that's not quite right for some reason, and then you'll kind of intuit, your subconscious will work out there's something wrong, and it'll tell your conscious there's something wrong with this maths here, and it gets easier the more calculations you do, basically. So if you do take a step wrong, just take a breath, look at it again, and there'll probably be something easy like here where I missed out the bit that converts this voltage gain into decibels, and this number here obviously makes much more sense compared to this number, as this number does compared to this number because they're close to each other. And again, this bit about R pi and the transconductance, if you're not quite with that bit, I really encourage you to go back and watch the linear power booster analysis because I did go into it in a little bit more detail in that video. So now let's calculate the output impedance, and then we can start measuring some of this using the oscilloscope and the signal generator. So let's calculate Z out. We've got RC, which is equal to 15K, and RV1, which is equal to 100K. And we can see that when we've got a full volume coming out of our pedal, so RV1's all the way up, then our Z out is equal to RC in parallel with RV1. So 1 over Z out equals 1 over 15K, which is the value of RC1, plus 1 over 100K. And if we put that into the calculator, so we've got 15 times 10 to the 3 to the minus 1 plus 100 times 10 to the 3 to the minus 1 equals, and then take the reciprocal of that, and we get 13K approximately. So it's approximately equal to 13K. So it's very close to RC, which is why people tell you that the output impedance of a common emitter amplifier is effectively RC, because it's so close. And you can use it as a quick approximation before you even do this equation. Now, when we think about it on the output, as we move that control, some of RV1 is going to be in series and some of RV1 is going to be in parallel. Now, the reason that we don't want it all in series is because we won't get any output, so the pedal would be effectively turned off. And when that is the case, we basically have 0 ohms as our output impedance. So we can say that Z out is effectively equal to 0 to 13 kilo ohms. But what we have to remember, and I've mentioned it in previous videos, is you're always going to have something following it, whether it's an amp or another pedal, or the input to another device, and that is going to be a load, and that is going to present itself in parallel to this output impedance of the panel. So this is always going to affect it. So we can effectively measure this, and we can move the control to the point where we still have a signal, and we can see how that decreases the output impedance. But once we turn it all the way and we're not getting any output signal, we can't then easily measure that using the method that I'm about to revisit. It was the same one we used in the linear power booster video, of course. So we can effectively say here that our output impedance is between 0 and 13 kiloohms in parallel with whatever load we present. So we could say between 0 and 13 kiloohms in parallel with any load is the output impedance of the Big Muff pipe pedal. So let's measure that, and then let's compare it to the actual green bubble font pedal and see if it comes out differently. So before we start making some measurements, let's just remind ourselves of how we do this. So I'm going to set up my function generator to 1 kilohertz. So this effectively needs to be a frequency that would be in the frequency range of what you were hearing. 1 kilohertz is a standard value, so we'll use that. And roughly an RMS that a guitar might output, so let's use 200 millivolts. So that's where I got those figures from. And I'm going to send that into a potentiometer, which is wired as a variable resistor. You can see how this is connected to this, which makes it to a variable resistor. And I'm going to wire that into, to measure Z out anyway, the output of the pedal, and that's going to go to the oscilloscope. But first of all, what I'm going to do basically is wire this from here to bypass it and just check that I've got 1 kilohertz, 200 millivolts on my oscilloscope screen. Once I've done that, I'm then going to wire it into the output. Note the input is not used in here. I'm not using the input at all, just the output. And then I'm going to take it to the oscilloscope. And what happens then is we dial down the potentiometer here until we get half or 100 millivolts RMS, as noted here. And because this is a voltage divider, and now we've got 200 millivolts in and 100 millivolts out, we all know that this value then should be equal to this value, because in a voltage divider, if these are the same, then you get half here between the two impedances in this case. So this Z question mark is the device under test, that's what DUT means, and it's the pedal in this case. Now, to save us a little bit of time later on, in order to measure the input Z in, what you do is you simply reconnect this to the input and you don't use the output. So you're literally just swapping this to the input. So I'm going to do both of those things now. I will probably start with the input of my pedal, and then we'll measure the output of my pedal, and then we will continue, and by my pedal I mean this one, and then we will continue by measuring the output of the actual green bubble font Big Muff pipe pedal and compare the results and also compare them to our calculations. So as you can see here, I've set up this 200 millivolts RMS, and we've got about a 1 kilohertz signal. I'm going to reduce this potentiometer here, so this reads 100 millivolts RMS. So it's going to be around there. Now what I'm going to do is take that potentiometer and measure it in the measuring device. So as you can see, 77.31 is really close to our calculated 76.53. So now I've got my function generator, 200 millivolts RMS connected to the output of the pedal here, and the potentiometer is all the way up. And what we're going to do now is decrease this potentiometer till we get 100 millivolts RMS. So I've gone way too far already. Bring this down more slowly. And I think that's as close as I'm going to get it, 109 millivolts. So let's measure that and see what that comes up with. So that's giving us 11.42K, which is close to our 0 to 13K, 13K with the volume all the way up that we calculated. And of course, with tolerances and everything, we're not going to get the exact figure. Okay, so now I've got the output connected to measure the output impedance. And again, RMS 202 millivolts and about 1K. And then we're going to reduce this potentiometer till that reads 100, and then we're going to measure the potentiometer. But this time I'm doing it with the output stage of this pedal. So it's around there. So I'm going to pop this out now. Put in my component tester. Let's see what we get. So we're getting around 12.35K, and we calculated 0 to 13K. So we are pretty close to that value, taking into account tolerances and everything like that. Let's measure the gain. So here I've sent my function generator into the input with a 1 kilohertz, roughly 100 millivolts peak to peak signal. That's reflected by the yellow channel here. And then the blue channel, which you can see is inverted and boosted, as you'd expect from a common emitter stage, is showing us about 392 to 400 millivolts peak to peak. So that's about a 4 times voltage gain, which is slightly lower than the 3.4 that we calculated in our calculations earlier. But as we know from before, for various reasons, such as component tolerances, things like probes loading the circuit when you're measuring it, and of course the limited precision of the equipment here, you don't quite get the same amount of gain out of these things as you calculate on paper, but it's close enough and it works well as the output stage of the Big Muff Pi pedal. So now let's have a look at the frequency response of the input of this pedal. So we know that our input impedance is approximately 76.5 kilo ohms, which is represented by this resistor here. And we've got a 100 nanofarad capacitor on the input forming a high pass filter. So what frequency does this pass at? So what I've done on Falstad here is I've measured it down here, and you can see I'm using the minus 3.01 decibels, minus 3 here. And it says it's approximately 20.84 hertz. But where did that figure come from? Well, we can do the maths as well, of course, on this. So it's the corner frequency, FC, equals 1 divided by 2 pi times the resistance times the capacitance. So in our case, that's 1 divided by 2 pi times 76.5 kilo ohms times 100 nanofarads. So nano is times 10 to the minus 9, and we know that kilo ohms is times 10 to the 3. So now we know that, we can enter it in our calculator. So we can say open brackets 2, and my pi is hidden here, so I'm going to press shift pi multiplied by 76.5 times 10 to the 3 kilo ohms multiplied by 100 times 10 to the minus 9, which is your nanofarads, close brackets, and it's 1 over, so I just do that to the minus 1, and it gives me approximately 20.8 hertz. Equals 20.8 hertz, which makes sense with this 20.84 hertz here. So we can also measure that, of course, or at least have a look at that on the oscilloscope and how it responds around that frequency. So it's passing basically all frequencies above where we can theoretically hear from, which is 20 hertz. And the reason it's doing that, of course, is because the tone stack is before this section of the pedal. So we don't want this section to then affect what we've set in our tone stack. Okay, let's have a look at our frequency calculation. So I've connected my function generator through the pedal to the oscilloscope. And earlier on, I put in a 1K signal and set this to 100 millivolts RMS. So what we're looking at now is the frequency. At the moment, it's 16.5 hertz, approaching about 70 millivolts, which is half the power, and seeing what frequency we register there or there. So as I bring this up towards 20, we should see it approaches 70 millivolts down here. So it's going to be around there. And you can actually see we're getting about 26 hertz, which is above the 20.8 that we calculated earlier, but that will be to do with component tolerances. And also we were looking at the input. I'm taking the signal here from the output of the pedal to show its whole frequency response. But what you can see is it's within the range of hearing and well within the range of the guitar, because this high pass filter starts operating around 20 to 26 hertz. So that concludes the analysis of the first section of the Big Muff Pi pedal, the output stage in this case, which is a common emitter amplifier with voltage divider bias and an emitter degeneration resistor. Now, we calculated in this video that the input impedance was 76.53K, and when we measured it, we found out that it was 77.31K, but do bear in mind the accuracy of some of these measurement techniques and the tolerance of the potentiometer, etc. So for all intents and purposes, it's roughly the same. We calculated the output impedance to be 0 to 13K in parallel with whatever we're plugging it into, an amp or another pedal, any form of load. And then we measured the unloaded circuit in my version, which is this one here that I've built up of the output stage, to be 11.42K. And then in this circuit, we measured it to be 12.35K. So again, very close to this ideal 13K. We did the gain calculation, and the DC analysis suggested that it was minus 13.14 decibels, or a voltage gain of 4.54. And then we redid that using some AC considerations, or small signal considerations, to give it another name. And that was 12.93 or 4.43 voltage gain. And remember, it's minus because it's an inverting amplifier, inverts the signal. Now, when we measured that, we got 4 roughly, and I ran the maths. 20 times log 4 gives me 12.04 decibels. So again, it's in the ballpark, and as we've seen before, you don't get the full gain from the circuit when you measure it for various reasons to do with component tolerances and other things. We then calculated the corner frequency, 20.84 hertz, checked it in Falstad, and then when we measured it, we got more like 25 hertz. But again, bearing in mind the precision of the equipment that I've got available here will also affect this. But I hope you can see that it's close enough to analyze and design circuits such as this one. And don't let any of this obviously stop you from building circuits like this, changing components, measuring stuff and playing around with it. This is where the fun lies, and this is when you get more serious and you want to sit down and design stuff later. But I fully encourage you, as I see many of you have been doing from the comments, to keep experimenting and keep playing around with these things. That's how we best learn, of course. Anyway, that concludes our look at the output section, and we'll come back to these other sections, the tone stack, the input section, and the 2 clipping stages in future videos in this series. Until then, happy experimenting. I've been Stu for Music Technology, and I'll catch you again soon.